Okay, good evening, one and all the participants for the fifth day of the FDP research avenues in using in biometrics using low cost devices. Today again we have yet another eminent speaker, Dr. SharadhaBhat. A brief introduction of Madam SharadhaBhat, a teacher by profession, has 30 years of teaching experience. Madam has worked in Government Arts and Science College, Karwar for 25 years and presently working as Associate Professor in Government First Grade College, Ankola. She has also taught PUC undergrad students and currently is teaching BSc students. Being a double degree holder, MSc in Mathematics and MSc in Computer Science, Madam has pursued a PhD in Computer Science from Mangalore University under the guidance of Dr. B.H. Shekhar. You will be listening to Dr. B.H. Shekhar on the first day of the offline session. Our research interests being image processing, pattern recognition, and biometrics, Madam has presented more than 20 articles at international conferences in various places of India, Russia, Malaysia, and published her works in Springer, IEEE, IS, PRS, ACM, and so on. Having executed her responsibility as head of the Department of Mathematics and Computer Science, she has also been the coordinator of IQAC and members of various committees and forums at college level. Madam has played a key role in organizing national and state level conferences and workshops in the college, and she is rendering her service for DC's Dream Project, Karnataka LMS, as moderator for e-content team of computer science at Karnataka University levels. Madam is, has membership in various bodies and so on. And very interestingly, Madam has authored a textbook for compulsory paper in computer applications for Karnataka University for BA and BSc students. Apart from her regular academic activities, she has also been an active member of Jilla Vignan Kendra Karwar, Bharat Vikas Parishad and Vanavi Kalyan Sangha. She has participated as resource person in many workshops and seminars and delivered lectures on mathematics, computer science topics such as image processing, artificial intelligence, machine learning, and biometrics. And today we are going to listen to Madam on yet another, a trait of biometric, that is on iris. Madam, the dais is yours.
Thank you, Bharti madam. Thanks for your kind introduction.
Thank
In
you.
fact, first of all, I wholeheartedly thank these organizers, Dr. R.K. Bharati and Harshita ma'am, because I'm actually honored to speak in this dais as I have my professor, my mentor, Dr. Shekhar is also speaking here in the offline mode. So I'm really happy to come here and spend some time with you all. Shall I start from the
Yes, madam. Yes,
sharing
please.
slide?
Yes, madam.
Okay, participants, uh, we shall have first 60 minutes about iris recognition system, various parts of it. Ma'am, is there any disturbance?
No, madam, but slides are not visible.
Okay, I have not shared it.
Okay, okay. No disturbance, madam. We are clearly audible.
Let me share the slide.
Mm.
Okay, now is it visible?
Yes, madam. Yeah.
Okay.
You have to go. Yes, madam. It's visible, madam. Mm.
Okay. So first 60 minutes or so, we will have some introduction to iris rate, iris, so different models of iris biometric iris recognition system. And then for the second hour, well, let us see some of the demo of some of the works which we have tried together. Uh, so these are the things we are going to do in this next 120 minutes. So I'll quickly go through these slides because the other 2 days on ear biometrics and trait, another trait, gesture, Professor Nagendra Swami and Professor Surya Kumar has spoken about this. So I'm not going to the details of basics of biometrics now. Uh, Let me tell you one thing about this authentication and identification scenario here regarding biometric systems. Iris is a well-versed authentication system, so it can be a best trait or best gate for authentication, biometric authentication system, rather than identification scenario. I'll explain that in the next slides why it is so. Regarding identification, see, in case of authentication, the person will come and he'll claim that he is so and so. But in case of identification, um, sometimes people are ready to be identified, like in biometrics, say attendance system as the first figure. They are ready to be identified as so and so. But sometimes they might not be ready to identify, like when they are frauding something, when they are when they want to steal someone else's identification, then they might not be identified. So in that case, iris won't be a very good trait to identify such persons. We have different biometric traits here, including iris, fingerprint, hand geometry, and so many other things. Like these are all physiological biometrics, or say based on human body structure or human, say, biological matters in the sense. And some of the biometric traits which are based on their behavioral pattern, maybe keystroke dynamics, handwriting, gait, and their voice, etc. Then, among all these biometric traits, why iris, right? The other day, Professor Nagendra Swami was speaking about the different, say, expectations, or um, say what we need with a biometric trait, isn't it? So, let me say, almost all the expectations are partly or in a way fulfilled with iris, because the first one, it is universal and yet distinctive. Say every universal means we want each and every person or each and every human being who want to be say identified or recognized under biometrics must possess that, isn't it? So everybody is having, every human being is having iris, so let us forget about those exceptional cases, okay? And still it is distinctive. Say it is unique for each individual. It has been proved that even iris of the iris for the twins is different, and iris for the the left and right irises of the same person is distinct, is different. So it is best one for a general, say, recognition and yet to be distinctiveness of it. For example, see, by looking at the image itself, we can say without any say software, by looking at the image itself easily, like face, we can say the difference between the two irises of the irises of two persons. Next, another expectation was permanent. So face can be, say, deformed according, as the age changes, isn't it? It's not stable over time. But iris is an age invariant biometric trait, I can say. There is a famous article. It's a how Afghan girl was identified. You can type in Google. It's an interesting article. See here, her face has been changed a lot after 15 years, but iris is the same. So this is an article in National Geographical magazine that proves iris is permanent over um, time, I can say. Another important thing is it is quantifiable or measurable. Now, what happens in case of iris is, when you say identify, when you localize the iris pattern, it can be converted into a rectangular shape iris templates. So it is size invariant. So while converting it, while transforming from the iris ring to rectangular shape, you can set its size as a fixed one. So it is a fixed size invariant rectangular shape, and hence it has got significant mathematical advantage, we can say. It's because of its permanent size, right? And the iris is formed with the in like during the birth itself. In fact, during the um, fetal development, it is formed. So, hence, the furrows, wrinkles, and ridges of iris are developed randomly, I can say, and making it highly invariant for um, intra-class variables, where with the variations or dissimilarity score with it's very high with a um, interclass, and it is very low with the intra-class. This is because of its structure. So it's we can say it is better performing biometric trait. And another one thing was, another expectations about this biometrics was, most of the people should like it. People should not deny this giving their biometric detail. This is fine with iris biometrics because people need not have to touch the physical device. There is no physical device to be touched when you are taking the iris photo. Like if it is a fingerprint, you have to touch the device, but with a face and iris, that is not there. So it is visible, non-invasive, and an internal organ. And then it is fraud resistance. Like face can be you in case of face biometrics or in case of fingerprint, people can use the different maybe a photo of the face, or fingerprint can be modeled, like. So that is not the case with iris, and hence less threat, or no less spoofing attacks in case of iris biometrics. So these are all the reason why iris can be taken as one of the best say biometric trait. Or even I would rather say iris, when you consider it in one of the modalities in multimodal biometric system, then it will be very this can be taken as a very good modality. So this is the structure of the human eye. And let me show you what is taken as the uh, which part of the eye is taken for our say iris biometrics. This is the pupil part, darkest area of the eye, and this part is the light or white part, lighter shade of the eye. This is called as sclera, and the bit in between these two, pupil and sclera, we have this part of the human eye that is taken for iris biometrics. And this part is used for this pupil is contracting and dilating, isn't it? So that part, that is done by the muscles in this iris part, and hence it has got that structure, the different structure, wrinkles, ridges, and all. And this part is this is called iris ring. Actually, this part is taken for iris biometrics. Now this is common in any of the biometric system actually, and that is the same with iris biometrics. Let me quickly go through this. Suppose this is your query iris, IXY is your query axis, and for a person, for an unknown pattern, unknown person X, and IA is the iris pattern which is stored in the gallery. Let us assume this is a gallery image, or this is an unknown image, query image. And let us assume that using a distance metric D, we have calculated dissimilarity score. Let us assume D is a dissimilarity score between these two patterns. Then an authentication system, or in a way, every biometric authentication system is a binary classification system, as we all know. So there will be a threshold tau, and if you are distance is less than this threshold, it, the person is accepted as x is accepted as a, and if this distance is greater than that threshold, he will be rejected, right? Similarly, identification is a multi-class classification system wherein this our system, the identification system may generate more than one say templates which are which are uh, having this value less than the threshold t, and among them the smallest one is accepted, smallest one is taken and checked. If that is matching with this class, then the person is belonging to the class ci. Suppose if there are 100 people in the say system, then there'll be 100 class plus another class is n plus 1th class, which is if none of these values are less than the threshold, none of the dissimilarity scores are less than the threshold, then the person is classified into this n plus 1th class, means he is not identified, isn't it? So this is our authentication and identification system. Now, in iris recognition system, we have these many stages. There are actually 5 stages. Um, See, here I have listed 4 stages because the first one, or you may say the 0th one, is iris image acquisition. Let me talk about that later. Let me start with, let me assume that the iris images are taken and we have a data set of iris images. Then let us talk about iris localization, normalization, feature extraction, and representation and code matching. So coming to, okay, this I'll skip. Fine. There are 2 stages in any recognition system. One is the stage of enrollment, wherein you collect all the iris images and normalize it, extract the feature, turn it into an iris code, and store it. That is enrollment. Store it. Of course, there must be a line here. Store it along with the name ABCD, etc. And then in the second stage, when the person claims, this picture is authentication system. When a person claims his identity, again generate the iris code using all this say process, then match with this, or say search with the stored database. In fact, in case of authentication, this stored database is of lesser size, but in case of identification, it will be a bigger database. So match with the codes, iris codes here of person, the same person, and if the match found, he is accepted, otherwise he is rejected. Now come to localization. This is, say I have an eye image here, eye image wherein the region of interest is taken. Okay. With this eye image, we have to find out the region which is which can be a candidate iris region. We have to find out that. Right? And after this, isolating this image, the important another important thing is these circular boundary parameters are to be calculated, like a pupil iris at the radius of the pupil and radius of the iris. Similarly, center of the pupil and center of the iris, this is looking the same in this figure, but most of the times centers are different. Pupil and iris boundaries are not concentric in most of the time. So localization is a step wherein you find the part of the iris which is the candidate iris part, and the region which is the candidate iris part, and then you calculate the boundary parameters. This is what is needed in this stage, we can say. Next, let me explain one system which is doing this job, iris localization. This is a good old system, and this person is Dogman, J. John Dogman. He can be referred to as father of iris biometrics. He This was his paper in early 90s. He has got patent for his work on iris biometrics, and till 2008 that patent was there, and after that remaining people have actually started working on iris. So this is famous integro differential operator of Dogmans, which is used for iris localization. What this method does is he takes the integration on a contour, yes, of the input image. Here x naught and y naught are supposed to be the center of the contour, and r is the radius of that contour, and after that his derivatives are taken at each step, and then a Gaussian function is used to smooth it. Okay, this is the procedure followed by Dogman for several years. Later the researchers have developed different kind of operators. I'll explain that later. um, and the another one is circular Hall transform, which is very much used in um, iris localization, especially finding the parameters, boundary parameters. Here, an edge detection tool is used. Maybe some of the researchers are using recently other edge detection tools also. Earlier, Richard Wildes was using the first derivative itself as using Gaussian filter. He used to say he has detected the edge for this iris, and then he has used circular Hall transform. Means this we all know that this circular Hall is transform or a tool is a voting tool. So you identify the edge pixels first, or you coarsely identify the edge pixels, and then you find out when then you vote it whether it is an edge pixel or not. So based on this equation, say where this xc and yc actually here are the center of the circular part, and this is the radius, so that this part should be here it should be yj, and here it should be yc. Okay, this there is a mistake. This part should be 0. So this, when it is 0, this is a candidate pixel. Okay, this pixel is on the circle. So using this tool, Ho transform, most of the, and this is the most popular say tool in iris localization. Then we have iris normalization. So the first step is iris localization. You have the input iris image, and you come up with these two circles. Okay. After this, we have iris normalization. So when we have say we are having these iris boundary parameters, then this is something like, so this is an iris ring. Start with any point here, any point on the pupil, or take any direction. I mean, you make a slight cut here, and then unwrap it to get the formula, something like this. Got it? This is an iris ring, got a small cut here, maybe this axis, and then unwrap it. Okay. This is done by having a polar transformation, a different type of polar transformation, and it's called unwrapping the iris ring. And again, the Dogman is the first one to call it as rubber sheet model. He was the first one to introduce it. These are the say equations. And are these xp and yp, xp yp is a point on the pupil, and similarly xs yx is a point on the iris, a point on here, another point here, and theta varies from 0 to 360. You can even vary it in a smaller scale, and this r varies from rp to ri. R varies from this part to this part. Okay. So these two equations will convert this ring type structure into a rectangular shaped iris template, and along with the x-axis we can have angular values, theta values, and along with the y-axis we can have so this is called angular axis, and this is called radial axis in case of iris. This is the boundary, the one with the boundary parameters, and you take a varying r means you take a smaller and smaller circles along with this, and so this is the unwrapped iris. These resolution are depending on how smaller part you are taking here, how smaller is your theta while taking the while unwrapping, and how smaller is your r while unwrapping. So that is the, so this iris part, sorry, this iris part, this, in fact this is not exact part which we need, but this is the one which you got as a ring, iris ring, that has some occlusion that we will deal with it later. So this part is unwrapped and we got this iris template. So this is the second part, normalization part. And after this, when the iris is, right, when the iris is localized and when it is unwrapped, something like this, after that we need to extract the features from this. Now actually the feature extraction work starts here. Okay, in fact this is same for all the other biometric traits, isn't it? After you get the region of interest and then start feature extraction, and after this you go for representation. Several methods are discussed in the several methods are published, several feature extraction techniques are said in the literature's review. The phase based, zero crossing, texture based, etc. So let us discuss one or two here: phase based and zero crossings. Uh, this is Dogman's phase encoding, or this is a phase based method, Dogman's phase encoding, or 2-bit encoding using Gabor wavelet. So this is how it is done. You use the Gabor wavelet equation, and we all know that with the input iris, I r theta, after this wavelet transformation, after this filter, it is, we get the um, the real part and imaginary part of this input values, isn't it? For each pixel, input pixel, we'll have a real value and we will have an imaginary value. Correct. So his method is encoding this each pixel into zeros and ones using this process. If the imaginary value is greater than 0, he encodes it as 1. If it is less than 0, it is encoded as 0. So that's why it's called as phase encoding. That to 2-bit encoding. Each input pixel is explained in terms of 2 bits, either 1 1 or 0 0 or 0 1 and 1 0, based on the real and imaginary values, whether positive or negative. So since it is based on zeros here, it is called, also called as zero crossings method. This is the iris, input iris, unwrapped input iris for feature extraction, and this is 2-bit Gabor encoding. Okay, so after using the filter and we get, and encoding the iris, we get a template something like this. So this is a, you can say this is a matrix of zeros and ones simply, right? So input iris, unwrap, and we got the iris code now. Okay. Before we getting into this, before we try to get the iris code, or even after getting the iris code, there is something called noise removal strategy, because you can see this iris, unwrapped iris here, or it's also called as normalized iris. Uh, this part is for because of specular reflection, so this is not a good part of the iris. Similarly, these parts are not good parts. This is, so these are referred to as noise, and we have to remove this. So there is some strategy called as masking the noise. So what people do is they'll they'll put a mask here. They'll put a mask wherever there is, see, wherever there is a noise, a mask is mask is introduced, you can say, with the iris. So they'll have two patterns like this. One is iris, actual iris, and another one is its mask. Okay, so that this part is not considered for the future say processing. Another one is they're voting for the best iris pixel. So this iris this iris part is divided into smaller and smaller units, and each unit or each cell is so that we can vote it, we can give a weightage for this. Each cell is identified as iris, or it's a best iris, or it's not at all an iris, or it's moderate. It can be a little bit of it can be taken as iris, something like that. That's voting process. Another process is there using fragile bits. So a bit is called fragile if uh, s- if it's changing its value for different irises. I mean, the same person's different irises, the value is changing. For example, here is a bit 1, and for in another say template, the bit may be 0. So those type of bits are called as fragile bits. So the weighting of, or voting or giving the weights for iris regions is also done based on fragile bits. Okay. So these are some of the noise removal strategies of iris templates. Finally, iris code matching. There are several. So there are so many methods, so many processes explained in the literature, but I have taken some of the examples to discuss with. Okay, so Hamming distance is the one most popular method which is used with the binary iris code, I can say. So when you have two iris codes with binary values here, query iris and gallery iris, then this is also a matrix of zeros and one, and this is also a matrix of zeros and one. So that Hamming distance would be a best distance metric for to find the dissimilarity score there. Okay, so this is which is working with XOR um, say operator. Okay, so after finding this dissimilarity score, two irises which are of the same person uh, will have, because it is dissimilarity score, will have very less value here, so that is genuine score. And two persons or two irises with of different persons will have um, say larger value, and that is imposter score. Okay, so then with this dissimilarity scores, to evaluate the iris authentication system, we go for, mm, say, distribution of false acceptance rate and say false rejection rate, or you can say distribution of genuine and imposter scores here. This is called the philosophy of biometrics, universal at individual. Means, see, this part is um, the genuine score. Okay, and this part is the imposter score. So this is probability density function of imposter score. As you can see here, you move the threshold through this. As the threshold moves this side, false acceptance rate will be high. And if the threshold is moved this side, false rejection rate will be high. So something has to be done with the threshold so that you have minimum or minimum possible both the rates, false acceptance and false rejection rate. So this is one of the evaluation process for authentication system. If these two probability density functions are not overlapping at all, that is taken as the best authentication system. Okay, you can refer the according to this philosophy of biometric technologies, you can read more about this in this website, or this entropy system or probability density systems of these scores, and statistical independence of these biometric systems. You can refer this paper. It's a very well explained. Again, Dogman's paper. You can refer this. Another evaluation systems, these are already explained by Professor Nagendra Swami sir. ROC curves, and here we also use D prime values, whereas this is based on the D prime value is based on this distribution here. Say we consider the mean of this distribution, mean of genuine and imposed distribution. Similarly, sigma of this distribution, and then this D prime value is calculated with this. Mi minus mg is imposter and genuine scores means, and then there's standard deviation. So like that, D prime value. So as D prime value is higher, that is considered as the best um, biometric system, because their difference will be more, isn't it? Similarly, equal error rate, that's another one. So when you consider the DET curve, so where false acceptance rate and false rejection rate are same, that is called equal error rate. So for a best system, equal error rate should be possibly zero, very very less, and D prime value should be very very high. That that is that is an indication, or that is evaluation method for authentication systems. Okay, and this has been explained by Nagendra Swami sir. You can consider even ROC also. This line should be moved towards these two lines. Then it is considered as the best system. Uh, for this was for authentication system. Now for identification system, say we have rank one identification rate, means when when it is considering the threshold and all the dissimilarity scores less than the threshold are taken, there will be top T matches, isn't it? Among the top T matches, if the first one itself matches with the um, query iris, if the first one is the one which you are looking for, then it is called rank 1 identification rate. Okay, like that, all the ranks are taken here, and then the rank identification rates are considered, and that is called CMC curve, cumulative match characteristic curve. And the meaning of this is, if rank 1 is at 0.7, 70%, then the 70% of the identification attempts accuracy is found at the rank 1. Among all those attempts, it's that means this is a best one, isn't it? At the almost 70%, almost in the 70% of the search, we got rank 1 identification rate. That is the mean. So this is for evaluation of identification system. Then we can see we have publicly available data sets for iris. It's like face and fingerprint and all. We have IIT Delhi, Malaysia, MMU dataset, Cassia, UV iris, and there is something called mobile iris challenge evaluation. There are two things actually: iris challenge evaluation and mobile iris challenge evaluation. They have developed their own data set. If you want to take the challenge, you must you must test your algorithm with their data set. So these are the, and now one more data set is that is UAE, United Arab Nations. They are using iris in their say airports, and they have come up with a data set, UAE data set. Even in Cassia also we have mobile iris data sets. So these are some of the samples from sample images from these data sets. This one is, you can see here, IIT Delhi, MMU, Cassia. This is for Cassia V4 distance. There are versions of Cassia dataset, and this is a UBIS version 2. These are the images taken from the mobile, and even the dataset says whether that image is taken from iPhone or it is taken from Samsung mobile. something like that, or some app is downloaded and then the mobile image is taken like that. Let me tell you one more thing about this data sets. uh, so we have not touched upon image acquisition, isn't it, in the beginning? It's because, say, to collect the images, it is the collecting the iris image is, it needs a very careful engineering work, like very careful photographing, so that and that's mainly because iris is a comparatively smaller part in a human eye, in a human face, and our these eyelids are very sensitive, isn't it? So it is not so easy to take the iris images. These pictures are taken, these two, first two, including this, these are taken from near infrared cameras, special cameras, we can say. And this is taken with the usual camera, with the usual visual wavelength. So these are called NIR images, near infrared images. And this last one, UV iris, this is version 2. In version 1, they had NIR pictures, NIR images. But these are called as VW images, visual wavelength images. And challenges are there in both the um, imaging process, actually. Because as I already said, our eyelids, human instincts are more, eyelids are more sensitive, isn't it? So we are always don't keep our eyelids open, isn't it? It's not open, it's not like that we can open it always, something. So we have occlusion of eyelids here and eyelashes, you can see this part here, these images, occlusion with the eyelids, and people wear glasses here that may create the noise, something like this. Then sometimes this hair may come, isn't it? Like, no, I don't have a picture here. Sometimes this hair may occlude this eye part. Okay, and in case of VW images, these are all from NIR camera. In case of VW images, there may be occlusions. There may be illusions. I'm sorry, isn't it? Less, say, you can say bad image, less brightness. Okay, and then reflection of, this is more in a visual wavelength pictures. There will be reflections in the, see, this iris is in this iris part, in this image part, this part cannot be taken for the comparison or feature extraction. So this part is degraded, we can say, only this much is available. That's why I said in the beginning, uh, for identification this may not be a very good biometric trait, but this is a very good trait for uh, authentication. And these two are again visual wavelength, and these are all from the mobile iris. These are all taken from the mobile camera, but with a in NIR effect. Okay, this we have already discussed. Challenges in iris biometrics, occlusion by eyelids. Completely, iris is not. We cannot calculate that. Only we are getting only this part of the iris, and almost occlusion by the reflection, right reflection, occluded by the eyeglasses. Similarly, this is the bad illumination here. And there is one more thing. Sometimes the when it is case of identification, people may not be looking at the camera directly, so there may be orientation like this. This is completely damaged image. uh, Here also the iris image is not along the say not perpendicular to the image here, isn't it? Iris, so you can say this image is oriented or say deviated from its center part. And these things, these defocused or degraded images will cause, say, will make this localization and segmentation very difficult, and hence recognition rate will be reduced. This is the challenge in iris biometrics. So now we'll see iris feature extraction method using raise filters. See, I have explained here. Till now we have seen different stages of iris biometrics, right? Localization, and then normalization of the iris, and then feature extraction, finally iris code matching, and then different eye images with the various challenges in iris biometrics.